The speaker of the day, Mr. C. RAMeshBabu, who has joined us from AA College of Engineering and Technology, Shivagashi, to speak about an interesting topic, smart nano concrete and cement-based material. Before I introduce the speaker, let me just give you for 5 minutes an overall view of what is happening. As all of you know, that we have been customizing the cement for various applications, various types of concrete, various requirements of concrete, ranging from slump retention, ranging from different types of materials that is being used, blending material used at site, along with ordinary Portland cement. Different requirements like higher slump retention for RMC units is required. That is where we have customized our cement, and that is where you will get the RAMCO Infra 5343 grade cement. Then we have the precast application. In fact, precast segment, I think a lot of development is yet to take place. Of course, we have those conventional precast units across Tamil Nadu, Kerala, and other places where they make this hollow block, solid block, paving block units and all that. So for that, we have RAMCO Superfast RHPC, rapid hardening Portland cement, which gains compressive strength quickly. Then we have the Portland Pozzolana cement, as per IS 1489, we have 4 varieties of PPC cement, out of which, as all of you know, RAMCO Super Grade has been used in concreting application across the country. And last year we had launched RAMCO Supercrete, which is a cement specifically meant for concreting. Then we have the RAMCO Superfine, Karthik Super Plus. Then the Portland Slag Cement as per IS 455, RAMCO Super Steel, RAMCO Samudra, and the special cement, sulfate resistant Portland cement, the RAMCO Super Coast. So we have the 12 varieties of cement. Dry mix product, as all of you know, we have the dry mix range of products which is manufactured at our Sri Perambuduru plant, specifically meant for various non-structural applications. So if you want to fix your tiles, you can have the RAMCO tile fix, which can be made in a thin bed, and then it can be stuck to the walls or wherever it is to be applied. Then RAMCO block fix, specifically customized for fixing the blocks. The RAMCO Superfine, the tile grout, and other plaster related products that we offer from our dry mix plant. Of course, RAMCO Supercrete cement, which is a specially formulated cement which can give you a high rate of gain of strength as well as a low heat of hydration. That is what the speciality of the cement is. So that is why you will find that we have this, because basically we all talk about high performance concrete. So that is the reason why we have launched RAMCO Supercrete, and it has been used in various kind of concreting applications, and they have got excellent feedback. Of course, the basic thing is high compressive strength, high workability, and durability, which are the hallmarks of RAMCO Supercrete cement. Then the RAMCO Research and Development Center, which does a lot of work in the area of cement and testing of cement and other blending materials, as well as conducting concrete mix design on various grades of concrete with usage of various admixtures and different types of sand. Of course, M sand, as all of us know, is being used in various parts of the country because river sand is not available. So what we have done is that we have done a lot of concrete mix design using M sand for various grades of concrete, and we have been able to get excellent results. So we have been checking the various types of M sand. Of course, one must not use M sand which is having a high percentage of dust, because that can lead to a lot of shrinkage cracks. So we have been doing a lot of work on that, checking the durability of concrete, which is not very common, but of course some of the researchers, some of the concrete projects do demand for it, especially to check the permeability of concrete, which indirectly measures the durability of concrete, which can of course be measured using the amount of charge that is passed through the concrete specimen. So for example, if the amount of charge that is passed is greater than 4000 coulomb, it is subject to deterioration, and if it is less than 2000 coulomb, considered to be acceptable, because the impermeability of concrete is very high, and you will find the concrete is able to resist the attack of sulfate, chloride, or any other kind of attack. So that is the reason why we check the durability of concrete. Then we have the water permeability test using the DIN code, wherein we check the permeability of water through a concrete specimen. It can be either, as you can see from this figure, it can either be a concrete cube or it can be a cylinder, and then water can be passed through the specimen at a high water pressure, which can be determined as to what water pressure has to be. The different projects have different specifications, and The requirement is that, of course, the permeability of water should not be more than the cover to the reinforcement bar. So that is the basic idea of having this test. And of course, the concept of right product for right application is what we follow. We try to understand the requirements of concrete from the site and then specify the right type of cement. So that is the idea of having this. And then RAMCO Cement has been able to get a lot of awards, especially the 4 Leaves Award, which has been given for leadership in technology, energy efficiency, usage of blending materials. Very important because without usage of technology, it is very difficult to get good quality cement. And of course, various customers like Larsen & Toubro, Tata Housing, ITD Cementation, various institutions, the metro projects who have approved our brand, various projects in the eastern part of the country who have been using our cement. So that is what all about the RAMCO cement that we have and the initiatives that we have taken in the recent past. Just to give an introduction of today's speaker, Engineer Ramesh Babu. He is having more than 14 years of experience in teaching civil engineering. He received his BE Civil Engineering from NIT Durgapur and ME Structural Engineering from MEPCO Engineering College, Shivagachi. He then served in various prestigious institutions, including Shastra and MEPCO. Currently, he is working in the AA College of Engineering and Technology as Associate Professor. He delivered numerous guest lectures and webinars on soil mechanics, disaster management, steel structures, strength of materials, optimization techniques, nanotechnology in civil engineering, and ANSYS software. He had published 12 research papers in international journals and conferences, including Archives of Civil Engineering, American Institute of Physics Advances, AIP Advances, and AIP conference proceedings. He authored numerous manuscripts on applications of nanotechnology in civil engineering. Also, he had authored a chapter in the book Smart Nano Concrete and Cement-Based Material for Elsevier publications. Currently, he is doing PhD in nano composites and submitting thesis to Anna University, Chennai, and is on the verge of completion of his doctoral degree. He is a prestigious member of ICI, ISTE, and ACI. So with those introduction, let me invite Engineer C. Ramesh Babu to start off with his presentation for today. You can share the presentation because on the third icon is a presentation. Mr. Ramesh Babu. And so the thing is that it is very interesting to see that as I was discussing with him, a lot of development is taking place in concrete technology, and this specific topic on nano concrete and cement based material, I am sure that we need to understand the development that is taking place so that we can apply our mind and see whichever aspect is in the research stage can we implement it at site and how effectively we can implement it. So with those few words, let me invite Mr. C. Ramesh Babu over to you for your presentation on smart nano concrete and cement based materials.
Yeah, thanks a lot, Dr. This is RAMCO Babu, Associate Professor from AAA College of Engineering and Technology. I take this opportunity to thank RAMCO for inviting me to provide a technical talk on smart nano concrete and materials. Once again, I am glad to get this opportunity from RAMCO. So thanks a lot, sir. And let's go through the lecture smart nano concrete and cement materials. Actually, the lecture is based upon the topic publications for the book Smart Nano Concretes and Cement Based Materials. So here goes the lecture. The nanotechnology definition, the material comes to give structures a size in the nano range. So this is a definition from chemistry. It says that nanotechnology is a technology which forms structures using atoms and molecules in the range of size of the range of nanometer range. The materials that possess one is by colloid science, polymer chemistry. The materials formed as permanent of from bulk materials. So we can manipulate the properties, we can manipulate the material properties, we can manipulate the size of the materials and by varying their dimension in nano range. in the scale range, if you vary the properties, you get whatever materials or properties like, because nanotechnology is an as we know that millimeters is 3, micro is 10 power minus 6 meters, nano is 10 power minus 9 meter, pico is 10 power minus 12, femto 10 power minus 15, and atto 10 power minus. There are two different top down to make the what you want. So whatever we want, we can make from top down up. We can have a big chunk and cut it whatever we want by cutting them into smaller particles. And bottom up technology is the technology where smaller atoms or molecules are assembled to form prefabricated units, and from the prefabricated units we can form the desired property of the structures that we like. What is nanometer? It is if the distance between the sun and the earth were 1 meter, then the football field would be 1 meter long. So if the distance between sun and earth were 1 meter, then the football would be 1 meter to 1 nanometer long. So it says nanometer length, and the comparison between nanometer and the distance between the sun and the earth is stated here. The diameter of the human hair is around 10,000 nanometers. 3 atoms of solid material is approximately 1 nanometer long. There are 5 grams of nanoparticles in this jar. So though for every person on the earth, we can have 3 million each. So imagine the size of nanometer. The jar itself, it contains nanoparticles. Only 5 grams of nanoparticles are present in the jar, but each and every person on the earth 3 million each. So imagine how smaller a nanometer could be. The study of controlling the matter at an atomic and molecular scale is said to be nanotechnology. Nanotechnology deals with structure size between 1 to 100 nanometer in at least one dimension, and involves developing or modifying materials or devices within that size. Nanotechnology was first introduced by physicist Richard Feynman in his famous lecture in a meeting of the American Physical Society at California Institute of Technology in the year 1959. So nanotechnology is not a newer technology. It's all about 4 to 5 decades prior to our thinking that nanotechnology, the term was invented, and it was shared by physicist Richard Feynman in his speech in 1959 at California Institute of Technology. However, after 2 decades, it was defined as manufacture of materials using sizes and accuracy between 0.1 to 100 nanometer by Drexler. Therefore, this is not a new science or technology, but became a hot research topic in last 2 decades. Hence, nanotechnology refers to the development of devices, structures, and systems by controlled manipulation of size and shape with at least one typical dimension measured in nanometers. So this was told already that we can enable the size and shape as the typical dimension measured in nanometers, and the enabling technology enables us to manufacture structures with the nano dimension. And based upon nanotechnology, the molecular units are converted to giant units, so that changing the property at nanoscale enables a promising technology at the macroscopic scale. So this is all about the comparison of scale of things, nanometers and more. Imagine that the human hair is 10 to 50 micrometer wide, fly ash is 10 to 20 micrometer wide, and ant is 5. A dust mite is about 200 micrometer in dimension. So red blood cells are 2 to 5 micrometer in dimension. So all pictures provided in this slide shows you about the difference between nanometer, micro. So 1 lakh, 10 lakh nanometers make 1 millimeter. So imagine how small the size could be, and manipulating the properties of the materials at such smaller size will give an enabling technology at millimeter dimension. Here is a small example of the usage of nanotechnology. The scientists from Taiwan have invented that by injecting gold nanoparticles into the leaves, they could make the trees bioluminescent, making them natural street lights. So the trees will glow at night because the nano gold particles are injected into the trees. so that there is no need for street lights, and we can have these trees for light at night. The nano concrete, so what's a nano concrete? A nano concrete is nothing but it's a concrete made by filling the pores of traditional concrete using nanoparticles of size less than 500 nanometers. So imagine that whatever particles you are using, if they are less than 500 nanometers to produce concrete, such a concrete is said to be nanoconcrete. The nanoparticles of silica turn into nanoparticles of cement in the chemical reactions that is in the concoction of the concrete. So nanoparticles of silica. So silica, nano silica, if you mix nano silica with the concrete ingredients for making nano concrete, the nanosilica nanoparticles will provide chemical reactions that takes place in variety of ingredients of concrete. It enables particle packing theory, and it also enables the denser concrete, so that by filling the micropores, it provides a denser concrete. What are all the advantages of nanotechnology or nanoconcrete? High compressive strength concretes of 15 MPa and 75 MPa can be achieved within a day. So imagine that we can achieve high compressive strength concrete of the range 75 MPa only one day. So on single day itself, we could achieve 75 MPa strength, and 45 MPa and 90 MPa at 28 days, and 48 MPa and 120 MPa at 120 days. So such a promising future is there for nanotechnology and nanoconcrete, that within a day we can achieve 75 MPa. High workability with reduced water cement ratio. Use of super plasticizing additives is unnecessary. So no need to use super plasticizing additives unnecessarily. It fills up the micropores and micro spaces, and cement content is saved up to 35 to 45%. Advantage of nanoconcrete is it stops the contamination caused by microsilica solid particles. The lower cost per building site. If you use nanoconcrete, for the building site, lower cost is enabled, and concrete with a high initial and final compressive and tensile strength are being produced, and concrete with good workability is produced. No need for using plasticizers, and also lung disease, silicosis risk is stopped. So all these are advantages of nanoconcrete. Nanotechnology in construction industry is ranking among 8th of the 10 most significant areas of application. Although nano products are costly, the research of nanotechnology is gaining momentum with the motivation of immediate profitable return from high value products. So even though nano products are costly as claimed by so many people and researchers, nanotechnology is gaining momentum with the motivation of immediate profitable return and high value products. So we can get high value products using nanotechnology. Nano products have the ability to manipulate the structure at nanometer scale, which leads to the generation of tailored multifunctional cementitious composites with superior mechanical performance and durability, having a range of novel properties such as low electrical resistivity, self-sensing capabilities, self-cleaning, self-healing, high ductility, self-control of cracks. So all these kind of enabling technologies could be achieved, novel properties which could be achieved by using nano products. So we have generally problems that occur in the site, that is shrinkage cracks is unavoidable. So cracks due to brittleness is also unavoidable. So we can improve the ductility by nano reinforcement by using nanofibers, copper nanotubes, nano bridging organic and cementitious materials, transformation, strain softening material to strain hardening material through the use of new generation nanofibers. So we can have good strain hardening material using new generation carbon nanofibers. Crack formation due to dimensional instability from thermal and moisture fluctuation, that is shrinkage cracks. The shrinkage cracks could be reduced by means of suitable nano products and nanotechnology. Then insufficient resistance to chemical attacks such as alkali silicate reaction and delayed reaction of ettringite and sulfate attack, ettringite formation, delayed ettringite formation, sulfate attack, corrosion, freeze thaw, etc., primarily due to high permeable nature of concrete. The nanotechnology products and nanoconcrete reduce the permeability by proper utilization of nanotechnology, self-repair, sealing, admixtures, self-healing, use of nano products, interface management, nano engineering of concrete pour solution, self-monitoring through use of nano products. The introduction to smart nanoconcretes. Concrete is one of the most important and ubiquitous materials. Concrete has become the material of choice for the construction of structures exposed to extreme conditions as well as civil engineering devices. The global consumption for nanomaterials is expected to grow to 100 billion by 2025 with around 7% for construction materials. So imagine, dear researchers, imagine that the nanomaterial consumption is expected to grow by 100 billion by 2025 with around 7% for construction materials. However, the conventional concrete, we are facing a lot of inherent deficiencies such as low tensile strength. But if we reinforce them with nanomaterials, for sure we will get the nano concrete and concrete which is having high strength and superior strength and superior in tensile strength. And concrete can undergo significant, the conventional concrete structures undergo shrinkage cranking. So this could be overcome by using nanoconcrete and nanomaterials. Nanoparticles exhibit a high surface ratio that 1 gram of nanoparticle can cover a football ground. So such high specific surface area is being provided by outstanding chemical activity of the nanoparticles. They can also act as nuclei for cement phases. The nanoparticles also act as the seeds for cement phases, promoting cement hydration due to higher reactivity as nano reinforcement, and they also act as filler. Thus, nanoparticles could accelerate the hydration of cement, providing seeds for hydration, providing locations for hydration, increasing the compressive strength and tensile strength of concrete, and make the concrete more durable and impermeable. Various types of nanomaterials have been added to cement and concrete to modify the properties, such as nano silica, nano aluminum oxide, tetra zinc oxide viscose, nano zinc oxide, zirconium oxide, chromium oxide, copper oxide, calcium carbonate, nano titanium dioxide, copper nanomaterial, graphene, carbon nanotubes, carbon nanofibers, nanoboron nitrate. It was reported that these nanomaterials provide additional seeds for nucleation and crystal growth of hydration products, including the growth of CHS gel. So additional CHS gel are produced, calcium silicate hydrate gel are produced by using nanoparticles, and besides that, particle packing theory is ensured by feature of nanoconcrete and cement-based materials is greatly affected by many factors such as type and degree of packing of mixing constituent as well as wall effect, wedging effect, loosening effect, interaction, particle packing density, size distribution, volume fraction, the shape of the particle, mesostructure of cement-based material, the defects of particle packing, and models of particle packing. Results show that particle packing density is favorable for nanoconcretes and cement-based materials by means of mathematical models, theory, and technology. So nowadays, people think that it is not viable or feasible to use nano particles in concrete, but exactly the concrete produced by nanomaterials is viable and feasible and range and high strength, producing even higher Young's modulus even by using a smaller percentage of nanoparticles. Hence, the product and quality of nano enabled structures are improving every year as researchers produce results on increase in the modulus of elasticity as well as the drain shrinkage, improvement in shrinkage every year on nanotechnology. Regarding the environmental impacts, the cement manufacture contributes about 8% to 10% of global carbon dioxide emissions as well as contributing to the global warming. The recent study showed the importance of nanotechnology by replacing existing cement and concrete production with nanomaterials. This will lead to development of eco-friendly green concrete as stronger and more durable concrete. This would minimize the usage of natural resources and reduce the adverse effect on environment. So green concrete is possible by using nanotechnology as it reduces the global CO2 emissions as well as contribute to global warming. Now we will move on to properties of cement and concrete in presence of nanomaterials. Materials having size less than 100 nanometer are said to be nanomaterials, and the study of science of such materials is known as nanoscience. The interdisciplinary science and integrates with chemistry, physics, biology, materials engineering, earth science, computer science, and many others. Nanotechnology controls the shape and size at nanometer scale. The nanotechnology may modify the properties of the construction materials, particularly that cement and concrete. Nanotechnology can also reduce emissions, raw materials, and energy of structures. So it reduces emissions, materials, and energy of structures. So a very small quantity of nanomaterials are required for producing nanoconcrete. So, and also it reduces the CO2 emissions for producing green concrete, and it supports global warming. Concrete, the most important material in construction industry, consists of hydrate phases, additives, and aggregates, and suitable for nanotechnological manipulations. We can manipulate and play with concrete by varying the materials and ingredients of concrete by varying their sizes at nanoscale. Nano cement revolutionizes the construction industry, and Portland will become a high-tech material. The construction can be made faster, cheaper, safer, and more durable with nanotechnology. And if nano cement could be manufactured and processed, it will revolutionize the construction industry, and Portland cement will become high-tech material. What happens when nanosilica is added to the cementitious material? First of all, when you add nanosilica to the cementitious material, what happens is it reduces the carbonation. The carbon dioxide are controlled. It accelerates the hydration. It reduces the porosity. The microstructure becomes denser, and formation of additional calcium silicate hydrate gel is enabled, and it reduces the sulfate attack. What happens when nanosilica is added to cementitious materials? So we get additional calcium silicate hydrate gel on using nanosilica. So here is a chemical reaction that is representing the additional calcium silicate hydrate gel formation, and along with calcium hydroxide. So when you add nanosilica, what happens? There is a strength enhancement. It reduces calcium leaching. It increases durability. It accelerates the hydration rate. It refines the pore structure. So while adding nanosilica, you get all these advantages: strength enhancement, reduction in calcium leaching, increase in durability, accelerating hydration, and refine the pore structures. So pore structures are being refined when you add nanosilica. Effect of nanosilica on the heat of hydration of Portland cement. The effect of nanosilica on evolution of heat has been studied by a large number of. Here is a curve which represents the heat of hydration versus the time. First of all, you can see that the heat of hydration is divided into 3 parts. The first peak with intensity 0 to 2 is due to initial hydration occurring at the surface of cement particles, mainly on tricalcium aluminate. The second peak is due to the hydration and consumption of tricalcium silicate, forming calcium silicate hydrate and calcium hydroxide. The third peak corresponds to the formation of calcium sulfate type, monosulfate and ettringite. It is reported that nanosilica provides larger nucleation sites for hydration. It is referred by researchers that acceleration is due to shearing effect also. Thus, the accelerating effect of nanosilica may be due to Pozzolanic effect. There is a marginal difference in the presence of 8% and 12% nanosilica, indicate that only an optimum amount of nanosilica is needed. In presence of nanosilica, the microstructure of the cement paste becomes denser, and it enables good particle packing. The microstructure of the cement paste becomes denser, and because of this mechanical properties increase. Some pictures shows large amount of calcium hydroxide plates with large porosity, and for 4% nanosilica with ultra high performance concrete, it gives a dense structure. The main hydration product in the presence of nanosilica is a foil-like calcium silicate hydrate gel without calcium hydroxide crystal. Furthermore, in presence of 5% of nanosilica, lesser number of pores are observed. So on increasing the quantity of nanosilica, the pores get used. So microstructure of the cement paste becomes denser in presence of nanosilica, is the result that has been produced by the research. Here is some picture that is showing you calcium hydroxide flakes, and the second picture B shows you fine calcium silicate hydrate gel of dimension 10 nanometers, and the third picture shows you the reduced pores because of using nanosilica, 5% nanosilica, and it is an ultra high performance concrete. Chloride ion penetration becomes reduced when you add silica. So when you add nano silica to nano concrete, what happens is the chloride ion penetration is controlled, and the concrete becomes impermeable to chloride ions. Corrosion of iron bars in concrete can be caused by chloride ions. However, in presence of nano silica, the chloride permeability is reduced. Pore structure of the cement matrix is refined by nano silica. Electrical properties of concrete in presence of nanosilica. The conductivity of the concrete is related to porosity and high pH content. So when you use nanosilica, it has been observed that the concrete produced has higher resistance to electricity and lower permeability of ions in aggressive environment. 0.75% to 1.5% of nanosilica increase the electrical resistivity of concrete. It is observed that finer nanosilica perform better than nanosilica coarse when water to binder ratio is 0.35, and in general, initial hydration of cement normally occurs on the grain surface alone. As the hydration products increase, thickness of the surface of unhydrated cement grains increase and the hydration becomes slow. When nanosilica is incorporated in the system, pozzolanic reaction occurs on the surface of silica to form nanosilica. The amount of seeds formed is low. So calcium silicate hydrate seeds formed is low when you use low quantity of nanosilica. So the nanosilica usage of nanosilica should be increased to get more number of seeds for nucleation. And this means that to greater extent the hydration occurs at cement surfaces. So because of this, porosity of hardened matrix remains large. The porosity of hardened matrix remains large. When large amount of nanosilica is added, larger amount of calcium silicate hydrate is formed, making the structure dense. However, the main problem with nanosilica is agglomeration. So whatever I have told about nanosilica is okay, but anyhow, nanosilica produces agglomeration, which is a disadvantage, and this could be overcome by addition of small quantity of plasticizers and superplasticizers. Attempts should be made to find out large-scale dispersion method. So there is a question for researchers that a large-scale dispersion method should be adapted for nanosilica in concrete. Benefits of nanosilica in calcium silicate hydrate seed formation. You can see cement grains, and between the cement grains, nanosilica is present, and nanosilica form seeds for silicate hydrate gel. And the second picture shows the reduction in, and because of the because of addition of nanosilica, the pores gets lessened. The number of pores is lowered. So the porosity, if you use the nanosilica, the effect of nano zinc oxide, zirconium oxide, chromium oxide, copper oxide, calcium carbonate on cementitious system, these materials increases the mechanical property, they reduce the porosity. Nano zinc oxide increase the mechanical properties, reduce the absorption and porosity. Nano zirconium oxide reduces the percentage of water absorption and porosity of cement matrix. When water curing is done, along the optimum limit of nano chromium oxide was 1%, whereas 2% was when the curing was done with saturated lime water. So this is a research output where the curing with saturated lime water. So the optimum limit was about 2% when you cure when curing is done with saturated lime water, whereas it is only 1% when normal curing is done. It accelerates the hydration. So the basic benefit of nanomaterial is they accelerate the hydration units and also form nucleation sites producing hydration. Nano calcium carbonate accelerates the hydration, increase the flow times. Chloride ion penetration in concretes decreased in presence of nano calcium carbonate. Effect of titanium dioxide on the hydration of cement. The addition of nano into the system has drawn a lot of attention. Heat evolution and compressive strength in presence of 5% of nano titanium dioxide are enhanced considerably. In the presence of 3% and 5% of nano titanium dioxide, the pore size distribution is enhanced. it is seen that greater pore refining effect is found in presence of nano silica. The pore refinement may be due to the formation of additional calcium silicate hydrate gel. So due to the formation of additional calcium silicate hydrate gel, the pores get reduced. In titanium dioxide is affected by optimization of calcium silicate hydrate gel structure. It improves interfacial transition zone and pore structures. It also controls nanoscale cracks, improves early strength, and decrease autogenous shrinkage through nucleating effect. Nano copper material on properties of concrete. The copper nanomaterials have been used in electronics, catalysis, and biology, but their use in construction industry is limited. The copper nanomaterial enhance thermal conductivity for antimicrobial and anti-corrosive coatings, etc. on concrete surfaces. Nano boron nitride. The properties of reactive powder concrete are due to particle size, low porosity, and dense microstructure. RPC, when combined with nano boron nitride, shows excellent properties. So you can imagine that if you use nano boron nitride in concrete, it leads to low porosity and dense microstructure. Concrete, when you use these microelectrical mechanical systems, when they are into the matrix or on the surface of the concrete, they act as sensor for detecting the. So you can have live strain readings on using the sensing devices in addition. Chloride ions and pH CNT system also has sensing. So if you imagine an impregnated matrix, they act as sensor for detection of strain in the structure. In addition, temperature, moisture content, chloride ions, and pH can also be monitored by sensors. Antimicrobial phases, generally silver is meant for these a number of antimicrobial nanoparticles such as naturally occurring chitin, chitosan, and some peptides, engineered nanomaterials, CNTs, fullerenes, and metals, metal oxides, when coated on concrete, kill the bacteria. So silver, titanium dioxide, zinc oxide, copper, and magnesium oxide, when coated on concrete surfaces, they kill the bacteria. These type of concretes can be used in hospitals. Microbial mechanism of nanomaterial that has been shown here. The nanomaterial damages the proteins in the living organisms, and the cell membrane wall is also damaged by the nanomaterial, and they also damage the DNA, and they interrupt the electron transport, thereby leading to the demolition of the microbes. This is an example that is from Lisbon. So in Lisbon, they have used church dives in Misericordia, constructed with nano titanium oxide, which is a self-cleaning cement. So this is a self-cleaning cement that has been produced by addition of nano titanium dioxide. Methods of grinding for ultra-fine cement. We make ultra-fine cement. We can have ultra-fine cement 500 nanometer particle as a nano cement concrete. It is reported that the fine cement of the particle size 2 micrometer can be produced by grinding of the cement using ball mill, vibration mill, Raman mill, mixing mill, air blow mill, stirred mill, and so forth. It is also reported that the milling processes increase the surface area of the cement particles, which in turn expose higher surface area of the cement for hydration reaction. As a result, rate of hydration reaction can be increased. So basically, in case of concrete, the specific surface area is the key term which is being concentrated. So imagine a nanomaterial having the surface area which is equal to the area of a football ground. So such huge materials are possible. Nanomaterials having high specific surface area, which could be made by grinding them in ball mill, vibration mill, Raman mill, mixing mill, air blow mill, stirred mill, and so forth. Particle size is about 220 nanometer. Though numerous research investigations have been executed producing ultra-fine cement using top-down physico-mechanical grinding approach, very to produce nanoscale cement particles. Hence, with the aim to produce ultra-fine cement using physio-mechanical crushing method, bead milling technique was used. The following summarizes the effect of bead milling process to produce ultra-fine cement of particle size 220 nanometer from ordinary Portland cement having size of 10 to 30 micrometer particles, as mentioned in the case study. So you can imagine that the particle size of ultra-fine cement is of range 220 nanometer, whereas the ordinary Portland cement, the size of the particles is 10 to 30 micrometer. Case study on ultra-fine cement production by top-down nanotechnology concept. The case is the processing, characterization, properties of ultra-fine cement. The study reported the production of ultra-fine ordinary Portland cement from microparticles of ordinary Portland cement using bed milling, bed grinding. It's a type of stirring mill. So it's a type of, you can see the beads, the discs are provided at the rod, and there is a separation gap, and there are various compartments. Of cement particles was performed by abrasive and shear forces developed in the mill as grinding force. A schematic horizontal bed mill is represented in the figure. So this mill, a horizontal bed mill for producing ultra fine cement particle of the sizes of range 200 nanometer. In this milling process, the comminution of cement particle depends on several parameters such as grinding media, grinding force, agitation speed. In this case, grinding of cement was done at 3600 rpm, agitating speed in presence of two grinding agents, methanol and ethanol, for different times such as 1 hour, 3 hour and 6 hours, and describe in detail the comminution OPC particles by bed milling process to produce nanoscale particle. So you can imagine that methanol and ethanol are used for producing ultra-fine cement of size 200 nanometers. So in the grinding in presence of methanol for three different times for 1 hour, 3 hours and 6 hours. Characterization of ultra-fine cement is the particle size distribution, oxide composition, chemical phases, and microstructures were analyzed using laser particle size analyzer, and scanning electron microscope were used for studying the characterization of ultrafine cement. It has been observed that the following is the particle size of Portland cement before and after the bead milling process. The particle size distribution of OPC possesses 2.43 micrometer, 12.57 micrometer, and 38.77 micrometer respectively for 10, 50, and 90% of OPC particle. While significant reduction of the particle was observed after 1, 3, and 6 hour bed milling OPC, irrespective of the grinding agents used methanol, and they produce additional calcium silicate hydrate gel. The 10% of cement contains 110 nanometer of the cement contains. So after grinding in bed milling, it has been observed that 10% of the cement contains 110 nanometer particles, and 90% of the cement contains 330 nanometer particles. In fact, the particle size of 50% OPC is reduced to 240 nanometer and 200 nanometer after 3 hour and 6 hour milling respectively in presence of ethanol as grinding agent. It is also reported that the cement particle less than 500 nanometer can be termed as nano cement. Prior to this investigation, very few researchers have attempted to produce ultra-fine cement using grinding or milling method. Therefore, it is considered that the bed milling process is an effective technique to reduce the particle size of OPC to nanoscale level. So to conclude, to produce ultra-fine cement, bed milling method is the most optimal method that has been preferred by the researchers, because prior to this, not so many researchers have used the method for producing ultra-fine cement a particle size of range 220 nanometers. So after using the methanol and ethanol, they were able to produce 110 nanometer particles which are present in 10% quantity, and 90% of the particle are containing about 330 nanometer particles. So the research concludes that the bead milling method is the best method for that could be used for producing ultra fine cement and nano cement. Synthesis of cement. The production of cementitious materials. It could be produced by sol gel method by preparing aqueous based high density gel of nanosilica and low density gel of hydrated alumina through the reaction of sodium aluminate and sodium hydroxide at 9 degrees Celsius. The source of gel materials such as silica source and alumina sources were left undisturbed for 24 hours to ripen following mixing together using turbine machine. You can prefer sonication for the sol gel method. So high density gel of nanosilica and low density can be used through the reaction through sodium aluminate and sodium hydroxide, and they could be they could be using sonication for 3 hours, and it could be oven dried for 15 days at thus the uptake was then washed with distilled water and filtered off using membrane filter, followed by oven drying for 6 hours at 105 degrees Celsius and grinding to obtain powder. Usually, the Portland cement contains 3 main components such as silica, aluminum oxide, and calcium oxide. However, synthesized material contained only silica and aluminum oxide. The dried powder was treated with calcium nitrate solution to increase the calcium oxide content. Finally, the sample was allowed to centrifuge and filtered off, followed by oven drying at 105 degrees Celsius for 3 hours and grinding to obtain alternate cementitious material. The following figure represents the of alternate cementitious material nano cement synthesis procedure. The steps followed in this method avoid the use of high temperature and calcination that may lead to minimizing energy consumption and CO2 emission as well. See here, this is the procedure. Nano aluminum oxide and are allowed to ripen for about 15 days. Sodium hydroxide is added for hydrolysis and polymerization, and after the hydrolysis occurs in both the solution, they are allowed for ripening for about 15 days. Then they are mixed, the low density gel is mixed with the high density gel, and on evaporation the nano cement is produced. So this is a simple procedure that has been researched by scientists for essence of nano aluminum oxide and nano silica by using hydrolysis or polymerization reaction in presence of sodium hydroxide. They use the sol gel process. The low density gel is mixed with the high density gel, and on evaporation it yields nano cement. So here the physical properties and chemical composition of alternate cementitious material and nano cement by hydrothermal method and commercially available. See, OPC, the particle size range is 10 to 30 meters, specific gravity is 3.15, fineness is 2800. But in case of alternate cementitious material, the particle size is 0.167 micrometer, specific gravity is 2.11, fineness is 35,82,400 centimeters square per gram. And the calcium oxide content is reduced, and sodium oxide is produced at an composition of 5.31 percentage, and silica is present at 42.8 percentage. Aluminum oxide gets increased to 21.9 percentage. Magnesium oxide gets reduced. Ferric oxide gets reduced, and these type of chemical composition could be possible material or ultra fine cement content. So it's an attention to the civil engineering researchers in order to use the nanomaterials in construction sector effectively. Researchers and investigations are required to find out various facts like performance of nanomaterials and their reactive mechanism with composite materials like cement. The preference of nanomaterials with possible use in construction sticks and behavior of the building elements that have nanomaterials under different loading conditions. The nanomaterials used in civil engineering they are meant for composites, lighter structure, enhanced properties of cementitious materials, low maintenance coating, better pipe joining materials, better heat and sound insulation, improved reflectivity of glass, water repellent, self-cleaning and anti-fogging surfaces, ultraviolet light protector, nano-sized sensors to monitor construction safety and structural health monitoring, solar cells. So for all these applications, we can use nanomaterials. So here are some of the examples of utilization of nanomaterials. Carbon nanotubes, they are used for improvement in mechanical strength, thermal mechanical properties, efficient electron mediation. Silicon dioxide is used for enhancement in mechanical strength and durability, anti-reflective and heat isolation. Titanium dioxide is used for non-utility power production, anti-fogging, hydrophilicity, fouling resistance, self-cleaning capacity, rapid hydration. For rapid hydration, you can use nano titanium dioxide. And nano ferric oxide is used for improvement in mechanical strength and durability. Copper oxide improves the mechanical strength and durability, enhanced weldability and corrosion resistance of steel. Enhancement in mechanical strength. Zirconium oxide, improvement in mechanical strength. Zinc dioxide, improvement in mechanical strength. Calcium carbonate, enhancement in mechanical strength. Chromium oxide, improvement in mechanical strength. Silver, antimicrobial properties. So as I told you earlier, these compounds have been covered earlier, and their main purpose is improvement and enhancement in mechanical strength, including flexural strength, tensile strength, compressive strength, and torsional strength. Most of the researchers are with the improvement in mechanical strength by using these nanomaterials. Copper nanotubes. The copper nanotubes are widely used nanomaterials and getting attention of, in the field of application of nanotechnology in civil engineering. The copper nanotubes are the allotropes of structure. These cylindrical carbon molecules have unusual properties which are valuable for nanotechnology, electronics, optics, and other fields of materials science and technology. And here you can imagine the slenderness ratio of the carbon nanotubes is 1.32 into 10 power 8 is to 1. It is significantly larger than that of any other material. So such a huge aspect ratio, you can imagine, it's not slenderness ratio, sorry, it is aspect ratio. Such a huge aspect ratio, it enables the material to arrest the cracks at nanoscale, and also it forms as an impermeable material, leading to avoiding the shrinkage cracks form. The carbon nanotubes are 100 times theoretical strength that of steel, with specific gravity being 1/6 that of steel. Elastic strain is 12%. Young's modulus is 1 terapascal, and tensile strength is 200 GPa. The carbon nanotubes have huge strength, including the tensile strength as 200 GPa. Imagine such a huge tensile strength, 200 GPa, than that of steel. When compared with steel, the tensile strength of the CNTs are 1,000 times. The CNTs have been found to be used as reinforcing fibers, improving tremendously the mechanical properties of any other host material. Are members of fullerene structure family. Their name is derived from their long hollow structure within the walls, one-atom thick sheets of carbon called graphene. These sheets are rolled at specific and discrete angles. Of rolling angle and radius decides the nanotube properties. For example, whether the individual nanotube shell is a metal or semiconductor. The nanotubes are categorized as single-wall nanotubes and multi-wall nanotubes. Individual nanotubes naturally align themselves to form ropes. So here also, due to van der Waals force, agglomeration of carbon nanotubes occurs, and specifically the pi stacking. Applied chemistry, specifically orbital hybridization, best describes the chemical bonding in nanotubes. Bonding of nanotube involves entirely sp2 hybrid carbon atoms. These bonds are similar to those of graphite and stronger than those found in alkanes and diamonds. So imagine that the bond in CNTs are stronger than that in carbon atoms in diamond and alkanes. So this picture represents the picture of diamond, graphene, nanotube, and fullerene. The diamond is having sp3 hybridization, graphite is having sp2 hybridization, and nanotube is one-dimensional. Fullerene is zero-dimensional. The graphite is of having a single sheet having sp2 hybridization. From the graphene or graphene sheets, we can manufacture nanotube. One or two atoms having slightly different energies to give same number of new orbitals called hybrid orbitals having the hybridization occurs during the formation of compounds from atoms. So here you can imagine that the beryllium fluoride undergoes hybridization to form two different kinds of hybridization. Here 1s and 2p orbitals mix together to give 3 sp2 hybrid orbitals. This type of hybridization is called sp2 hybridization. In barium fluoride, in boron fluoride 3, boron undergo sp2 hybridization, as there are 3 sp2 hybrid orbitals lie at the corner plane triangle. The structure of boron trifluoride orbital is triangular planar with bond. These are the examples of hybridization. You can imagine that there are 2 kinds of orbitals and they produce 3 sp2 hybrid orbits. So these are also the hybridization process having the sp3 hybridization. The carbon nanotubes are divided into 3 types, that is the armchair and zigzag. So this is armchair. If m is equal to n, this is armchair structure of carbon. Zigzag n, 0, spiral n, m. So these are the 3 kinds of carbon nanotube structures. Carbon nanotube are 0.5 to 1.5 nanometer in size. Multi-walled carbon nanotubes are greater than 100 nanometer in size. Single-walled carbon nanotubes, the price of carbon costs around 1,000 rupees per gram. So, in the picture shown here, it represents rupees 4,200 per grams, because the single-walled carbon nanotubes are costlier, and because the manufacturing process is involves huge costs, and because of the manufacturing cost, the cost of single-walled carbon nanotubes is around 4,200 per gram. So it is costlier to use it for in construction. We can use nanofibers to arrest the cracks. The initiation of micro cracks could not be arrested, and the delay in macro cracks could not be avoided. However, we can arrest them with using nanofibers and material. Due to scarcity of knowledge in application of nanotechnology in construction industry, sufficient funds for executing researches on industrial application, structural applications. For high-rise buildings and massive structures vulnerable to aggressive environment, seismic activities, and global warming, there arise an urge to rely upon needs alternative material to develop sustainable construction industry. CNTs would be ideal material due to enhancement in high strength, ductility, crack freeness, and durability. They also have been found to be stable in aggressive environment. Of CNTs are the carbon nanotubes of Young's model 1 terapascal, tensile strength is 200 GPa, yield strength is 63 GPa. The CNTs have 5 times the Young's modulus of steel, 100 times the strength of steel, while 1/6 lighter than the steel. Elastic strain has been around 60 times greater than steel. Also, the CNTs are highly flexible, having high yield strength and lightweight. The CNTs adhere to forces. Several researchers saying that there exists inadequate bonding between the CNTs because of agglomeration and due to van der Waals forces. This could be avoided by using surfactants, and the flexural strength enhancement has been found to be 25% when you use CNTs in concrete, and the increment in Young's modulus has been found to be 50%. They also improve the thermal conductivity and thermal stability of the composites. A review of the results says that about 0.1% to 0.2% of CNTs is enough to be used in cement matrix, as patented by the United States of America. The Brenner et al. Suggests that 0.2% was optimal percentage of CNTs to be used in concrete matrix and cement matrix. The national status, there are various institutions including NIT Jalandhar using carbon nanotubes in their researches, but most of the researchers use powder mixing method and ultrasonication for mixing carbon nanotubes with the concrete or cement because of agglomeration, the carbon nanotubes get clogged together. To avoid this, you can use surfactants. The compressive strength has been improved by 8.5% due to powder mixing, and 22% increase in compressive strength by aqueous mixing method has been observed. The summary recommends that the nanomaterial size is equal to the size of calcium silicate hydrate gel. So this is a major advantage. If you use nanomaterial, additional calcium silicate hydrate and also the nanomaterials form seeding sites for the calcium silicate hydrate gel. The cement gains its strength from high specific surface area. When you use nanomaterials, high specific surface area are provided by nanomaterials, and it leads to accelerated hydration and strength enhancement. The nanomaterials form seeding sites for hydration of cement. CNTs offer good load transfer by enhancement in flexure and toughness, but the surfactants needed to be added to prevent agglomeration of CNTs. Disentangling techniques, how to disentangle the carbon nanotubes in cementitious matrix. You can use water with gum arabic. You can disperse it with the sulfuric acid and nitric acid. You can disperse in ethanol, and you can go for sonication. These are the various techniques that has been suggested. You can use super plasticizer for proper mixing. You can go for aqueous mixing or ultrasonication, or you can go for ultrasonication and super plasticizer, or ultrasonication and surfactant. The flexural strength modulus of velocity improved by 25 and 45%. If you use nanomaterial, the modulus of velocity gets improved by 50%, and flexural strength gets increased by 25%. Based upon ultrasonication, it has been observed that even if you use 0.048% of single wall carbon nanofibers, the flexural strength gets improved by 50%, and Young's modulus get improved by 75%. So here are some of the results where the compressive strength has been improved by 50% in presence of carboxylic acid and ultrasonication and polyacrylic acid. You can also use acetone and ultrasonication and surfactants. Here again, it talks about the silica fumes or microsilica, the byproduct of silicon ferrosilicon alloys. It has a huge surface area, 20 meters square per gram. Imagine the surface area is 20 meters square per gram, and the particle size in the range of 100 to 200 nanometers. It has been observed that addition of silica fume could increase compressive strength, tensile strength, and abrasion resistance compared to reference samples. Porosity produces a concrete more durable and resistant to chemical degradation process like chloride ion diffusion, alkali silica reaction, and calcium leaching. Furthermore, several nanosilica significant advantages are produced by nanosilica when you compare it with the silica fume. So instead of silica fume, we can use nanosilica. It is evident from the research that the incorporation of nanosilica with silica fume or fly ash could considerably enhance the mechanical strength by filling the tiny pores between the cement particles and silica fume or fly ash. Conversely, the flowing characteristics of fresh concrete may be affected due to the large surface area of nanosilica, which decreases the amount of lubricating water. It is essential to use some super plasticizer with nanosilica so as to avoid in fresh concrete. Nanosilica can be used for production of fire protective glass. This is achieved by providing a layer of nanosilica in between two glass panels, which in turns into dense and rigid fire protector. Therefore, these glass panels contain exterior light as an anti-reflection coating and hence conserve the energy. Tricalcium silicate hydration in presence of nanosilica. The effect of nanosilica hydration of tricalcium silicate has been studied. It has been found that in presence of nanosilica, the total height evolved is increased, calcium hydroxide consumption and CHS formation increased in presence of nanosilica. So as I told you, the C3S, the Bogues compound C3S, C2S, C3A, and C4AF, they are doing prominent role if you go and add nanosilica in or nanocement in nanoconcrete. So C3S is meant for airly strength. It produces more heat of hydration. C2S is responsible for 7-day strength, and it provides much of the ultimate strength. It is responsible for lateral strength of the concrete. It produces best hydration. The C3A reacts with water quickly. It leads to immediate stiffening of the paste. It is called flash setting. To avoid flash set, 2 to 3% gypsum is added. So these are the basics of cement hydration that has been pointed out for a better understanding the nanoconcrete. The effect of zinc oxide, zirconium oxide, chromium oxide, copper oxide, calcium carbonate on cement is 1 to 2% is produces the mechanical properties, porosity. Connectors, and they could be added to tiles, windows, cements, paints, etc. because of sterilizing and deodorizing properties, and when included in outdoor construction, it can considerably decrease the concentration of airborne pollutants. So if you want to reduce the pollutants, you can go for nano titanium dioxide nanoparticles to windows, cements, and paints because of sterilizing and deodorizing properties. It could also be used in infrastructure projects like pavements, tunnels, and buildings. Furthermore, that it has been reported that nano titanium dioxide particles can be used as partial replacement of cement in concrete matrix. It is observed that strength and durability of high performance concrete, high performance oxide particles also improve the mechanical strength, and also they decrease the setting time and increase the workability. Copper the crystalline copper oxide at early age of hydration of cement is increased, and larger amounts of calcium silicate hydride gel is formed if you use copper oxide nanoparticle. However, more than 4% addition of copper oxide nanoparticles reduce the mechanical strength and increase the porosity of concrete. So you have to add copper oxide within a range of 4%, lesser than 4%. If it is more than 4%, it leads to a formation of pores and it reduces the mechanical strength. Improve the particle density of mixed cement. So to improve the particle packing and the density of the cement, you can, and also for producing larger amount of calcium silicate hydride gel, you can provide nanoparticle. You can provide aluminum oxide nanoparticles, zirconium oxide nanoparticles, strength and decrease the setting time and workability. Particles, they improve the flexural strength and pore structure of self-compacting concrete and recover the negative effects of polycarboxylate superplasticizer. If you want self-compacting concrete, you can use zinc dioxide nanoparticles. They recover the negative effects of polycarboxylate superplasticizer. Also, the cement could be, you can replace the cement with nano zinc dioxide particles, a limit of 2%. So you can replace the cement by 2% of zinc dioxide nanoparticles, which could produce the additional flexural strength and pore structure of self-compacting concrete and recover the negative effects of polycarboxylate superplasticizer. Calcium carbonate nanoparticles, it has been found that they accelerate the rate of hydration setting to compressive strength. So calcium carbonate nanoparticles improve the compressive strength. They also accelerate the rate of hydration and the setting time. The setting time is also accelerated by means of adding calcium carbonate nanoparticles. The optimum content of nano calcium carbonate is observed to be 1%. It has been observed that concrete containing 39% of fly ash and 1% of nano calcium carbonate as replacement of cement showed enhancement in strength and durability properties compared to the control concrete. So you can use only, so as I told you earlier, nanoparticles could be used within a range of 2% whenever you want nano concrete or self-compacting nano concrete, and also you can use the fly ash along with the nanoparticles. Chromium oxide nanoparticles, the chromium oxide nanoparticles, they improve properties of. It has been found that when cured in saturated lime water, it produces higher mechanical strength and durability properties when compared to the tap water at all ages. If you cure it with the saturated, curing is done with saturated lime water, this chromium oxide nanoparticle produces concrete with good mechanical strength and higher durability. Silver nanoparticles has been found to be inactive pathogenic for active in paints to inactivate pathogenic microorganisms and give antimicrobial properties to the surfaces, for instance, hospital walls. You can use silver nanoparticles for coating hospital walls. This is because silver nanoparticles have inherent properties to reduce the growth and multiplication of fungi, viruses, and bacteria, which causes itchiness, infection, odor, and sore. The environmental aspects says that the only disadvantage is that we may of demolition or harm may be caused when the nanomaterial reinforced structures are demolished or destructed. So this is the only disadvantage. It may be potentially hazardous material, or it can show antibacterial properties. If you demolish the structures impregnated with nanoparticles, it may lead to lung damage or cell membrane respiratory functions. and damage of etc. So this is the major environmental aspect that should be taken care of. This is the chapter I have wrote to smart nanoconcretes and cement-based materials by elsewhere publications. I have proposed to use macroscopic carbon nanotubes as promising reinforcement. Instead of steel reinforcement, we can use macroscopic carbon nanotubes as reinforcement in concrete structures. This was proposed smart concretes and cement-based materials. I have published a paper in reinforced concrete structural elements. So how to used and how to utilize these CNTs as reinforcements in RC structures. So all these type of things have been covered in this paper. The conclusions of using nanomaterials. The addition of nanomaterials constantly reduces as well as final setting time of cementitious composite. This is due to large specific surface area. So as I told you earlier, nanomaterials have large surface specific surface area, more number of atoms on surface which are highly unstable and active, and consequently speed up the cement hydration reaction and eventually reduces the setting time. The addition of nanomaterials considerably reduces the workability of cementitious composites. So we have to use the surfactants or superplasticizers having a huge surface area. However, this can be overcome by using superplastics and supplementary cementitious materials. So if the workability is lost, however, workability could be regained by using the surfactants or superplasticizer. Cementitious composites are significantly improved the amount of nanomaterials. This is mainly because of the fact that nanomaterials act as ultra fine aggregate, which not only fills the tiny voids in composite but also act as kernel, which reduces calcium hydroxide and more consumption of calcium hydroxide and produce large quantity of. So this is one of the major advantage. The consumption of calcium hydroxide is high and it produces large quantity of calcium silicate hydrate gel. The mechanical strength and durability properties of cementitious composite were found to be decreased at higher doses of nanomaterials. So at higher doses of nanomaterials, the mechanical strength gets reduced and durability properties gets affected. So we have to use only a low dosage of nanomaterial. We should not use a higher dosage. Type and amount of nanomaterials to be added to the cementitious material. Challenges that impact on human health and environment and high cost. So these seek attention from scientific community working in this area. So it may be hazardous chemical to the environment when it is demolished. When structure impregnated with nanomaterial, when it is demolished, it may cause hazard to human health and environment, and also it costs higher. So we seek attention from more from the researchers working in this area. A novel use of nanomaterial has been suggested by so many researchers. The results of electrochemical tests clearly indicated the effectiveness of nanomaterials in controlling corrosion. The calcium nitrate inhibited as well as graphene and nanotitanium dioxide admixed cement slurry coating exhibited appreciable level of corrosion inhibition as compared to uninhibited systems. However, more tests are required for involving longer period of time to establish nanomaterials as corrosion inhibitors. So this is a vast area. Still, it needs more number of research and researchers to do research on nanomaterials to act as corrosion inhibitors. So far, the results are good as provided by the researchers worldwide working on the nanomaterials. So thanks a lot for hearing me. With this, I conclude nanomaterials. So what I want to convey is even though nanomaterials are costlier, we can have a lot of advantages such as improvement in Young's modulus up to 75%, even with the dosage of 2% of nanomaterial is possible, and higher mechanical strength are possible, and the lower porosity is achieved, higher durability is achieved. Anyhow, the hazardous chemicals that are generated by demolishing the structure is only the major problem by using nanomaterials in the nanoconcrete. Thanks a lot.
Thank you so much, Mr. RameshBabu, for that presentation. In fact, there was a few questions like if the compressive strength is high, even at one day, what about heat of hydration and what precautions we have to take? Are you able to hear me?
Yes, sir.
Yes, the video is yet to come on. to be switched on.
Yeah. Because if the compressive strength is high,
Yes, sir.
even at 1 day, does it mean heat of hydration is also high? That is one question being asked by Mr. Venkatesh.
Yes, sir. The heat of hydration is also high, but any use proper surfactants or superbasics that could be controlled.
Okay. Then like nano silica, can we produce nano GGBS and nano fly ash is another question.
Yeah, we can produce. There are so many methods for producing nano GGBS and nano silica.
How do we do that?
We can go for a grinding by balling method.
Okay. But it is very costly process, no?
It's costly process, but the improvement in mechanical strength and flexural strength are high, so that we can do those processes. It's still under research. Anyhow, we can go for those processes.
I think most of these materials under research state, I believe, no? Nowhere it is being utilized in large scale. Maybe on small scale, somebody would have produced.
Yeah, actually, the self-cleaning cement has been already used in Lisbon in a church. They have used self-cleaning cement, and that is one application that I showed you. And apart from this, it is at the research level. Only 28% all over the world scientists are getting funds for nanotechnology. So we need more funds for doing research on nano.
All right. Is there any separate code? I don't think so. Any separate code is there in Indian standard?
Not yet. There is no code at all.
Yeah. Thank you so much for that presentation on nano materials, Engineer RameshBabu, and thank you for sparing your time.
Thanks a lot, sir. It's a golden opportunity for me from RAMCO Cements. I take pride in thanking RAMCO Cements. I thank Mr. Anil Kumar Pillai from RAMCO Cements, Suraj Kumar and Vijay Kumar, sir. Thanks a lot, sir. Thanks for the opportunity. I would like to extend my gratitude from our college side, that is AAA College of Engineering and Technology, Sivakasi. Thank you, sir.
Thank you. So we meet tomorrow at 11 a.m. for a concrete lecture by Dr. Bhattacharjee of IIT Delhi. So we meet at 11 a.m. So till that time, all the best.
Thank you,
take care. Thank you so much.
Thank you.